Hello, dear students! We are now in the second quarter lessons in Mathematics 7. For Lesson 1, I will be discussing Introduction to Measurement. By the way, this is Teacher MJ Palara. Join me as we learn our lesson for today. Our most essential learning competency is for you, dear learners, to be able to approximate the measures of quantities, particularly length, weight or mass, volume, time, angle, and temperature, as well as rate. And for the references, it is listed down, but the primary source or the reference that I've used is the second quarter compendium of notes in Mathematics 7 by the Schools Division of Tarlac Province. Before we begin, let us do this activity. Let's investigate. As you can see in column 1, we have a series of questions, and in column B, we have the measurements. As you read the questions, what do you think are the measures that we have to find in order to answer them? I will give you some time to think and match column A with column B. All right, let's start with number 1. When we are asking how old are you, we are referring to measure of time. The answer in number 1 is D, or time. When we are asking how tall you are or how tall are you, we are referring to measure of or measures of length, which is letter B. Number 3, if we are asking how hot is it today, we are referring to temperature. Number 4, how much do you weigh, refers to measures of weight or mass. And for number 5, how much water may be filled in your tumbler? That question can be answered when we get the capacity or volume of the container. So for number 5, our answer should be letter A. With those examples, let us look at some of the other questions that we take in mind. Aside from those questions, we can also consider the following questions. For measures of length, we can include how tall, how far, or how long an object is. For weight or mass, we can consider how heavy an object is. For capacity or volume, we can ask how much can it contain. For time, we can refer to age or how long will it take someone to finish a job or other questions. And for temperature, we usually focus on the hotness or coldness. Okay, so we can ask how hot or how cold. With those questions, I know that you now have an idea about the definition of measurement. So you may think of some words that you can relate with measurement. Okay, but here is the definition as it was stated in our compendium of notes. Measurement is the process by which human beings obtain quantitative information about the different physical aspects of objects such as length, weight, area, volume, time, and temperature. The word measure comes from the Latin word mensura and from the Greek word metron. Now, we have two systems of measurement. The first one is the metric or the decimal system. For length, our base unit is meter. For weight or mass, it is gram. For capacity or volume, our base unit is liter or capital L. The other system of measurement is the US standard system or the English system. Here are the base units. For length, it is yard or YD. For weight or mass, pound or LB. Capacity or volume, its base unit is gallon or gal. Let us start with the measures of length. What are the tools that we use to measure length? Can you identify some? That's correct. So here are some of the objects that we use to measure length. And we can list ruler, tape measure, meter stick, triangle, and T-square, and other tools. Now, let us look at some of the most common measures or units of measures that we use in measuring length. For English measures, we have inch, foot, yard, mile. And for the metric measures, we have the following: millimeter, centimeter, decimeter, meter, decameter, hectometer, and kilometer. As you can see in the metric measures, our units have prefixes. We have milli, centi, deci, and we are just adding our base unit, which is meter. So for you to identify if a unit is metric or English, if you can see that it is using prefixes such as this ones, then that is already a metric unit of measurement. So again, remember that the base unit for English measures of length is yard, and for the metric unit of length is meter. Now, let us try to approximate measures of length. But before that, let us familiarize ourselves with the ruler. For instance, you have with you your ruler. So the lines here represent some of the measures that we have learned a while ago. For millimeter, you can see there the label mm. And these are the distances between these smaller lines is 1 millimeter. When we count 10 of those, so we will have 1 centimeter. That's why it is labeled there cm, that is 4 centimeter. And if you look at your ruler, that will end at approximately 30 centimeters. So you can say that a ruler, the standard ruler that we use, is approximately 30 centimeters. As for the inch, on the other side, so we have there 0, 1, as long as you can see the larger distances compared to that of centimeter, that is the measurement for inch. And a ruler's length is 12 inches. And 12 inches is equivalent to 1 foot. Take note of that. For us to visualize some of the real-life representations of our units, I will present to you some of the objects that we can use to approximate measures of length. For centimeter, you can refer to the distance between the tip of your finger from this point to this point. So that is approximately 1 centimeter. Okay, so you now have an idea of how 1 centimeter measures. How about an inch? In this example, we have a coin. If you measure the diameter of this coin, that will approximately measure 1 inch. So that is the approximate measure of an inch. For a foot, we can consider the length of a ruler, or if you have a pad or clipboard with you, so the length of that clipboard is approximately 1 foot. For yard, if you have a door in front of you, you just look at the distance or at the width of the door, and that is approximately the measurement of 1 yard. Okay, 1 yard. And meter is slightly larger because 1 meter is approximately about the width of 1.5 door. Okay, 1.5 doors. As for kilometer, now that you have visualized the length of 1 meter, or you just think of the length of a meter stick, if you are going to connect 1,000 meter sticks, you will come up with 1 kilometer. Can you imagine how long that is? Okay, so that is the approximation of 1 kilometer. Okay. And for a larger unit, we have mile, which is approximately 4 times around a track. This time, we move on to measures of weight or mass. Can you identify some tools that we use in measuring weight or mass? All right. So in this figure, we can see different types of weighing scales and balances which we could use to measure weight or mass. Here are some of the common units that we use in measuring weight or mass. For the English measures, we use ounces, pound, which is the base unit, ton, and metric ton. For metric measures, we again use the prefixes milli, centi, deci, deca, hecto, and kilo, adding our base unit, which is gram. So we have milligram, centigram, and so on. For us to visualize the measures of those units, let us look at some of these approximations. For the weight of a gram, imagine that you have with you a paper clip. That paper clip weighs approximately 1 gram. Okay, again, 1 gram. So if you have 1,000 paper clips with you and you try to weigh them, so the measurement or the weight of that 1,000 pieces of paper clips is 1 kilogram. Okay, with that, we can say that 1 kilogram is equivalent to 1,000 grams. That will be our lesson for next week. Also, a kilogram can be approximated through the weight of a kitten. So if you have a kitten, you try carrying that, and that is the measurement of a kilogram. or you can try in your kitchen. You try to look at 1 kilogram of sugar if it's unopened, or other condiments, okay, that weighs 1 kilogram, and you will have an idea of how a kilogram measures. The next one is volume or capacity. We have our English measures, our common English measures for volume or capacity. We have fluid ounces, cups, pint, quart, and gallon, which is our base unit. As for the metric measures, we have milliliter, centiliter, deciliter, liter, which is our base unit, decaliter, hectoliter, and kiloliter. Again, we are just adding the base unit liter to our prefixes. Okay? And for us to have a real life representation of those units, if you have a dropper with you, if you are going to get water or a liquid using that dropper and you drop it a little, so a drop of that is approximately 1 milliliter, or you can base 1 milliliter on the lines that you can see in the dropper. You can see there ml, 1 ml, 2 ml, and so on. As for a liter, if you are fond of drinking soft drinks, so you can see already that one bottle of a Coca-Cola or a pop measures 1 liter. So it is already written in the packaging, right? If it is 1 liter, 1.5 liters, or 2 liters. So now you have an idea of what a liter, or how large a liter is. That ends our lesson for week 1, wherein we've discussed how to approximate units of measures. For our next video, I will be discussing how to convert measurements from one unit to another, and I hope that you will watch that. For now, goodbye, and I hope that you continue to love math. Bye! Hello, dear students! Today we are going to learn converting measurements from one unit to another. For part 1, I will be discussing how to convert metric measures. Our most essential learning competency is for you to be able to convert measurements from one unit to another in both metric and English system. As for the reference, we will be using the second quarter compendium of notes in Mathematics 7 by the Schools Division of Tarlac Province. First, let us have a review on approximating units of measurement. I will be showing you some objects and we are going to approximate the measurement of each. For number 1, what is the approximate measurement of the width of a door? So the answer is B, 1 yard. How about the weight of a paper clip? So its weight is approximately 1 gram. Number 3, a drop of liquid is approximately 1 milliliter. For number 4, a person's weight is approximately 40 kilograms. And for number 5, the capacity of a bottle of cola is approximately 1 liter. So the answer for number 5 is letter A. This time, let us try to identify which unit is larger. First, is it kilometer or mile? The answer is mile, since 1 mile is approximately 1.61 kilometers. Next, is it decameter or decimeter? So the answer here is decameter, since 1 decameter is equal to 100 decimeter. Next, is it kilogram or pound? Which one is larger? So the larger unit is kilogram, since 1 kilogram is equal to 2.2 pounds. Is it liter or gallon? Which one is larger? So the larger unit is gallon, since 1 gallon is approximately 4.55 liters. And for the last one, which one is larger? Is it a milliliter or a cubic centimeter? The answer here is none, because 1 milliliter is equal to 1 cubic centimeter. And take note that in converting measurements, it is important that we know which unit is larger or smaller. Here is our rules in converting metric measures. So to change from a larger unit to a smaller unit, we simply multiply by a power of 10. On the other hand, to change from a smaller unit to a larger unit, we divide by a power of 10. We start by converting metric measures of length. So when we say length, it is a measure of how long an object is, or the distance between 2 points. Our commonly used metric units of length is kilometer, hectometer, decameter, meter, decimeter, centimeter, and millimeter. So for us to memorize that, we can use the mnemonics. Kim, how does Mike's dog catch mice? For letter K, we can use that for kilo, H for hecto, D for deci or deca, M for meter, D for deci, C for centi, and M for milli. So that is the arrangement of our prefixes. So again, when we are converting from a larger unit to a smaller unit, let's say for example, we are going to convert kilometer into meter. So we are going to multiply depending on the number of places that we have moved to the right. Okay, we'll have an example later. On the other hand, when we are converting from smaller unit to a larger unit, we divide. Say for example, if we are going to convert centimeter into hectometers, so we are going to count the number of places. So that is 1, 2, 3, 4. So we are going to divide the value of centimeters divided by 10,000. For us to have a clearer view of that, let us have the following examples. For example A, we have to convert 25 hectometers to decimeters. So first, we write our given, which is 25, and then we write its decimal point, which is at the end of 5 after 5, since this is a whole number. After that, we can use this diagram and locate hectometer, and we count the number of times we move to the right. So for every movement that is 10, another movement that will be 100, another movement that will be 1000. Okay, so again, hectometer to decimeter is 1, 2, 3. 3 movements to the right. That means that our decimal point will move 3 places to the right. When we do that, we will have 1, 2, and 3 places. Our decimal point will be here, but since there are no digits, so we have to annex zeros. That's why the result is 25 times 1000 or 25,000. So 25 hectometers is equal to 25,000 decimeters. For example B, we are going to convert 3.5 kilometers to meter. Our decimal point is already given, so we just have to find kilometer and meter in our diagram. So the distance between them is 1, 2, and 3. Okay, 3 places to the right, which means that our decimal point will also move 3 places to the right. When we do that, we will have 1, 2, and 3. So there are no digits in these two place values, so we have to annex 2 zeros. And our answer will be 3,500 meters. Or we can say 3.5 kilometers is equal to 3,500 meters. For letter C, we have to convert 6,210 millimeters to decameters. So again, we write our given, which is 6,210. And then its decimal point is at the end because it is a whole number. After that, we locate millimeter and decameter. So for this example, we are moving to the left. It means that our decimal point will also move to the left. So let us count how many places is that. So we have 1, 2, 3, 4. So 4 places to the left. Our decimal point will move 4 places to the left. So we have 1, 2, 3, and 4. Our decimal point will be here then. Okay, so our answer is 0.6210 decameters. This time, let us try to convert metric measures of weight or mass. So weight is a measure of how strongly gravity pulls, while mass is the measure of the amount of matter that objects are made of. And here are the commonly used metric units of weight. Again, we have the prefixes kilo, hecto, deca until milli, but this time our base unit is gram. Here are some examples on how to convert metric measures of weight or mass. For example A, we have to convert 26.5 or 26.75 kilograms to grams. So again, we write our given, which is 26.75. Our decimal point is between 6 and 7. So we just have to count the number of places from kilograms to grams. So we have 1, 2, 3. So we have 3 places to the right. It means that our decimal point will move 3 places to the right. When we do that, so we will have 1, 2, and 3. So we have to annex a 0 for us to have our final answer, which is 26,750 grams. For example B, we have to convert 145 milligrams to hectograms. Again, our given is 145. Our decimal point is at the end or after 5. And then we count the number of places from milligram to hectogram. So we have 1, 2, 3, 4, and 5. That is 5 places to the left. So when we do our movement, so we have 1, 2, 3, 4, and 5. Our decimal point will be here. Since there are no digits here, so we have to annex 2 zeros. So our final answer is 145 milligrams is equal to 0.00145 hectograms. Next, we move on to converting metric measures of volume. So capacity or volume. Capacity refers to the amount of liquid that a container holds, while volume is the amount of space inside a solid figure. Volume and capacity are related in the metric system because volume measures capacity. So in this diagram, we have here volume, which refers to the space, and capacity is the amount of water or liquid that could fill this container. And here are the commonly used metric units of volume. Our base unit is liter, and we have the same prefixes from kilo until milli. Here are some examples on how to convert metric measures of volume. So when we convert 7.5 liters to milliliters, we write our given. After that, we count the number of places from liter to milliliter. So that is 1, 2, 3. 3 places to the right. So we have 1, 2, and 3. Again, we don't have digits in this part, so we have to annex zeros. That's why our final answer is 7,500 ml. For letter B, we have to convert 3,500 centiliters to kiloliters. So first, we write our whole number, which is 3,580. Its decimal point is at the end. And then centiliter to kiloliter is 1, 2, 3, 4, 5. That is 5 places to the left. So our decimal point will move 5 places. So we have 1, 2, 3, 4, and 5. Our decimal point will be here. And we have to annex a 0. So our final answer is 3,580 centiliters is equal to 0.03580 kiloliters. For part 2, I will be discussing how to convert measurements from one unit to another, this time covering English measures. Please watch the next video for the discussion. Thank you. Here is the continuation of our lesson on converting measurements from one unit to another. For part 2, we will be focusing in converting English measures. Our most essential learning competency is again for you to be able to convert measurements from one unit to another in both metric and English systems. And our reference is the second quarter compendium of notes in Mathematics 7 by the Schools Division of Tarlac Province. For our discussion in converting customary units or English units, we will be using the dimensional analysis or factor label method. In this procedure, we will use unit fractions. When we say unit fractions, it has two properties, the numerator and the denominator, which contains different units, and the value of the unit fraction is 1. The following are examples of unit fractions. 1 foot over 12 inches, so those two are equivalent. 12 inches over 1 foot, 1 yard over 36 inches, and so on. Let's start with converting English units of length. So you should be familiar with the following conversions. In the first column, we have there the exact conversions of English measures. And for the second column, we have the approximate conversion from English to metric or metric to English measurements. Okay, so some of the common conversions that we use is 1 foot is equal to 12 inches. We also have 36 inches is equal to 1 yard. 3 feet is equal to 1 yard, and so on. Using those conversions, let us try to solve the following examples. For example A, we are going to convert 4 feet to inches. So for us to be able to do that, we have to find first the conversion for feet to inches or inches to foot. And we have here the conversion. 12 inches is equal to 1 foot. Using that, so we write our given, which is 4 feet, and then we multiply it with our unit fraction, which is 12 inches over 1 foot. So if you notice, 1 foot is written in the denominator part of our unit fraction so that we can cancel feet and feet. And we will be left with inches. Okay, when we simplify that, again, feet and feet will be cancelled. Now we can multiply 4 times 12. So 4 times 12 is equal to 48 over the denominator, which is 1, but we don't need to write that. So our final answer for example A is 48 inches. For example B, we are going to convert 180 inches to yard. Again, let us look at our table if we have a conversion for inch to yard. And we have there the conversion, 1 yard is equal to 36 inches. Using that, we again write our original or the number that we are converting, which is 180 inches, times the unit fraction 1 over 36, wherein 36 is in inches and 1 is in yard. And we can cancel inches and we can multiply 180 times 1 divided by 36. And the result is 5 yards. So our answer for letter B is 5 yards. And for the third example, we are going to convert 2.5 meters to feet. We write first our given, but we will use the conversion 1 yard is approximately 0.9 meter. So we have 2.5 meter times 1 yard over 0.9 meter. For us to cancel meter and meter. And when we multiply 2.5 times 1 divided by 0.9, the result is 2.78 yards. Next, let us move on to converting English units of weight or mass. Here are some of the common conversions that we use. 1 pound is equal to 16 ounces. 1 US short ton or capital T is equal to 2,000 pounds. 1 metric ton is equal to 2,200 pounds. 1 gram is equal to 0.035 ounces. 1 kilogram is equal to 2.2 pounds. 1 metric ton is equal to 1.1 US short ton. And here are some examples. We are going to convert the following to each indicated unit. For example A, we have to convert 4 metric ton to pound. And for the solution, we have to use the conversion 1 metric ton is equal to 2,200 pounds. Using that, we will have 4 ton times 2,200 pound over 1 ton. And we can cancel ton and multiply. So 4 times 2,200 is equal to 8,800, and then we write our unit, which is pound. So the final answer is 8,800 pound, or 8,800 pounds. For example B, we are going to convert 160 ounces to pound. So we identify which conversion are we going to use. From our table, we can use the conversion 1 pound is equal to 16 ounces. So 160 ounce times 1 over 16, and 16, that is equivalent to 16 ounces. And we can cancel ounce to ounce, and then we multiply. So 160 times 1 divided by 16, the result is 10 pounds. For the third example, we are going to convert 25.5 ounces to gram. From our table, we can use the conversion 1 gram is equal to 0.035 ounces. And we are left, or we have 25.5 ounces times 1 gram over 0.035 ounce. And we can cancel ounce to ounce. Then we multiply. So 25.5 times 1 divided by 0.035. The result is 728.57 pounds. So that is how we convert English units of weight. This time we are going to convert English units of volume. In our table, you can see there some of the common measures or conversions that we use for capacity or volume. And we proceed right away with the examples. For example A, we are going to convert 80 quarts to gallon. And the conversion that we will use is this. So we have 4 quarts is equal to 1 gallon. And we write our given 80 quarts times the unit fraction, which is 1 gallon over 4 quart. Then we cancel quart to quart. After that, we multiply 80 times 1 divided by 4. And the result is 20 gallons. For example B, we have to convert 5 pints to cups. So in our table, we can use the conversion 2 cups is equal to 1 pint. And we write 5 pints times our unit fraction, 2 cups over 1 pint. And then we can cancel pint to pint, and then multiply 5 times 2 divided by 1. The result is 10 cups. And for the third example, we are going to convert 100 milliliter to fluid ounces. From our conversion table, we can use 1 milliliter is equal to 0.03 fluid ounces. And we will have 100 ml times 0.03 fluid ounces over 1 ml. We cancel ml to ml, and we are left with 100 times 0.03 fluid ounces, and the result or the product is 3 fluid ounces. Next, we are going to deal with the measures of time and its conversion. So time is the ongoing sequence of events. It may be classified as past, present, and future. Also, the basic unit for time is seconds. And the common tools that we use in measuring time are the following. We have the alarm clock, stopwatch, hourglass, calendar, and sundial. In this table, you can see some of the common measurements or conversions that we use for measures of time. We use those to solve our examples. So for example A, we are going to convert 4 days to hours. So we know that 1 day is equal to 24 hours. So we just write our given 4 days, and then our unit fraction is 24 hours over 1 day. With that, we can cancel days to day, and then we multiply 4 times 24 divided by 1. The result is 96. So we can say that 4 days is equal to 96 hours. For example B, we are going to convert 300 seconds to minute. The conversion that we will use is 1 minute is equal to 60 seconds. So again, our given is 300 seconds. So in our unit fraction, seconds should be in the denominator, so that we can cancel seconds and we can multiply 300 times 1 divided by 60. The result is 5 minutes. For the third example, we are going to convert 25 years to hours. But for this example, we can not find an exact conversion from year to hours. So what we need to do is to convert years to days first, and then we convert days to hours. Okay, so here is the solution. So we write our given 25 years times our unit fraction. We are going to convert it into days. So we have 365 days over 1 year. And then we multiply with another unit fraction. This time, we use 24 hours over 1 day. Okay, so we can now cancel year to year, and then days to day. We are left with hours as the unit. So we multiply the remaining numbers. 25 times 365 times 24. The product is 219,000 hours. So that is the equivalent of 25 years. Next is converting measures of temperature. Temperature is a measure of hotness or coldness of something. Temperature is measured using a thermometer, and the basic unit for temperature is degrees. Here are some of the common tools that we use in measuring temperature, or different types of thermometers. So we have the electronic or digital thermometer. We also have the probe thermometer, glass bulb thermometer, the mercury thermometer, and the constant pressure gas thermometer. Here are the 3 temperature scales. We have the Fahrenheit scale, Celsius scale, and the Kelvin scale. In this table, you can see the most common conversions that you must memorize. So for the freezing point of water, it is 0 degrees Celsius. In Fahrenheit, it is equal to 32 degrees Fahrenheit, and that is equivalent to 273.15 Kelvin. For the normal body temperature, it is 37 degrees Celsius, or 98.6 degrees Fahrenheit, or in Kelvin, it is equivalent to 310.15. And for the boiling point of water, it is 100 degrees Celsius, or in Fahrenheit, it is equivalent to 212. And for Kelvin, it is equivalent to 373.15. Now, in converting measures of temperature, we use the following formulas. Okay, let us use those formula to solve the following. So for example A, we are going to convert 100 degrees Celsius to Fahrenheit. So for this, we are going to use the formula. Degrees Fahrenheit is equal to 9/5 times our temperature in Celsius plus 32. So using that formula, we are going to substitute the value of our given to degrees Celsius. So we will have 9/5 times 100 plus 32. So using Gemdar's rule, we first multiply 9/5 times 100. The result is 180. And then we add 32. So the sum is 212. And our answer is 212 degrees Fahrenheit. For example B, we have to convert 77 degrees Fahrenheit to Celsius. And the formula that we will use is this. So we have degrees Celsius is equal to 5/9 times the quantity degrees Fahrenheit minus 32. So again, we write our formula and then substitute the value of the temperature in Fahrenheit. So we have 5/9 times the quantity 77 minus 32. We simplify 77 minus 32 and then we multiply the result by 5/9. So we have 5/9 times 45. The result is 25. So we can say that 77 degrees Fahrenheit is equal to 25 degrees Celsius. And for the third example, we are going to convert 28 degrees Celsius to Kelvin. And the formula that we will use is this. So Kelvin is equal to degrees Celsius plus 273.15. We copy that and then we substitute the value of our temperature in Celsius. So we will have K is equal to 28 plus 273.15 and the sum is 301.15. So for our final answer, we say that 28 degrees Celsius is equal to 301.15 Kelvin. Lastly, we have the measure of rate. A rate is a special ratio in which the two terms are in different units. When rate is simplified, so it has a denominator of 1, it is called unit rate. Here are some examples. So we are going to find the unit rate in each case. For example A, a car traveled 300 kilometers in 5 hours. So for us to get its unit rate, we express it as a fraction first. So we have 300 kilometers over 5 hours. Since we have to have a denominator of 1, so we divide our given 300 divided by 5 and the result is, or we can cancel that. So we have 60/1 when we divide 305 by 5. So the result or the unit rate is then 60 kilometer per hour. So the car is traveling 60 kilometers per hour. For example B, we have Marie read 500 pages in 30 minutes. So again, we write it as a fraction. So we have 500 pages over 30 minutes. We divide them by 30. So 500 divided by 30 is approximately 16.67. And then we write our units, pages per minute. So Marie can read 16.67 pages per minute. And lastly, a painter took 6 hours to complete a job. He charged 240 pesos for his service. let us find the unit rate. And to do that, we just write it in fractions. So the amount, or that amount he charged over the number of hours he completed the job. So we have 240 pesos divided by 6 hours. When we divide that, the result is 60 pesos per hour. It means that his service is 60 pesos per hour. So that ends our lesson for week 2, wherein we've learned how to convert English and metric measures. As we end, let me leave you with this quotation by an anonymous author. As he said, "To convert a day is to convert a product." Again, to convert a day is to convert a product. Until next time, bye! Hi students! We are now on the third week of our discussion for second quarter in Mathematics 7. For part 1, we will be discussing translating English phrases to mathematical phrases and English sentences to mathematics sentences. Here is our most essential learning competency as well as our reference. And to begin, I have here a set of words. Can you group the following terms based on their relation to the 4 fundamental operations? Our 4 fundamental operations are addition, subtraction, multiplication, and division. If you have a paper, you can write them. Okay, I'll give you 15 seconds to do that. All right. So if we are going to classify those words, the words in red, or with the red words are under addition, the blue words are under subtraction. For multiplication, it is color blue, and for division, it is the pink words. Okay, and in a table, we have there the summary. So for addition, we have these terms: add, plus, sum. Additionally, we have the word more than and altogether. For subtraction, we have the word subtract, decreased, take away, less than, minus, difference, reduced by, and diminished by. For multiplication, we use the words multiply, times, product, of, or per. And as for division, we use the words divided by, quotient, shared, ratio of, split between, and of course the word divide. Here are some other terms and symbol that we will use in our discussion. This is the symbol for less than, the symbol for more than or greater than. This is the symbol for less than or equal to, or in short, at most. This is the symbol for greater than or equal to, or at least, and the symbol for not equal to. Let's start with translating English phrase into mathematical phrase and vice versa. We have here 2 columns. In the first column, we have the English phrase, and in the second column, we have the mathematical phrase. So for example number 1, we have to write the sum of 3 and 4. So it is in English phrase. If we are going to write that in mathematical phrase, we just have to identify the clue words. Okay, so in this example, we have the word sum, and we've classified sum under the operation addition. So we write that as 3 plus 4. 3 plus 4. For example 2, we have 10 decreased by 7. So again, our clue word there is the word or phrase decreased by. And decreased by is under the operation subtraction. So we write that as 10 minus 7. Next, we have the phrase a number less than 11. Again, a number less than 11. Since it is an unknown number, so we will use letter N to represent that number. And then we know that less than is under subtraction, and then we can write 11. But we have to remember that the subtrahend will be the quantity that comes before the keyword less than, and after it will be the minuend. It means that 11 is our minuend since it follows the word less than, and the number is our subtrahend. So our mathematical phrase is 11 minus n. For example 4, we have 6 times 5. So that is very easy. We just write 6 times 5, or for us to not get confused with the symbol for times and the letter x, we can use a parenthesis. So 6 parenthesis 5, that means that we are multiplying 6 and 5. Next, 12 split between 2. Split between means division. That means that we write it in mathematical phrase as 12 divided by 2, or another way of writing quotient is using fraction. So 12 is our numerator and our divisor. 2 is in the denominator. Next, we write 9 more than twice 8 in mathematical phrase. So before that, we have to write twice 8 first, and we can write that as 2 times 8. Okay, again, we can use a parenthesis to show the product of two numbers. So 2 parenthesis 8, that means 2 times 8. And we just add 9 because it says there more than. So we have 9 plus 2 parenthesis 8, or if you still want to use this symbol, the X symbol for multiplication, you can still use it. And for the last example, we have the product of a number and 2 divided by 3. It sounds complex, but we have to look carefully into the phrase. Okay, so a number is again represented by letter N, since we don't know what number is that. And then we have to multiply it by 2 because it says the product of a number and 2. When we do that, we can write that as 2n, or 2 times n, or 2 parentheses n. But since it is a number and a letter, so we just write it as 2n. Divided by 3, it means that we can write it in a fraction, so 2n over 3, or simply 2n divided by 3. Next, let us discuss translating English sentence into mathematical sentence and vice versa. For this one, we are going to include inequalities or the equal symbol. So that is the difference. For English sentence or mathematical sentence, we use equal to, not equal to, and the other inequalities, as well as the equal sign. But for the phrases, we simply write our expressions. For the first example, we write thrice a number less 5 is 60. Since we don't know the numbers, so we let x be the number. Okay, this time we use x to represent whatever those numbers are. Okay, First, we have to write thrice a number. So we write that as 3x, and then the term less is related or similar to subtraction. And then 5 is here, means that we have to get, or we use the equal sign to represent the word is. So if we are going to write that in a sentence, we will have 3x minus 5 is equal to 60. Next, a number minus 6 is 10. So in here, we have the term a number again, but since we don't know the number, so we let that be x. Minus means the minus sign, and then 6 is here is represented by the equal sign. So we have the mathematical sentence x minus 6 is equal to 10. For example 3, we have 6 added to 9 is 15. I think this is easier. We just have to add 6 and 9 to get the sum, which is 15. Next, 4 times a number is equal to 16. Again, we don't know what the number is, so we represent that as x, but we have to multiply it by 4. So we write that as 4x, and then is means equal to 16. So 4x is equal to 16. That is the mathematical sentence for this English sentence. Next, the quotient of 64 and 8 is 8. When we say quotient, that means division. Okay, and the word is again represented by equal sign. So the mathematical sentence is 64 divided by 8 is equal to 8. Next, we have twice a number minus 11 is greater than 20. We have there the phrase twice a number, that means 2x minus, for the minus sign, 11 is greater than. Again, it included the word is. It means that we will use the symbol for greater than, and then 20. So the mathematical sentence is 2x minus 11 is greater than 20. And for the last example, we have 3/4 of a number is less than or equal to 24. 3/4 of a number can be written as 3/4 times x. Then we have is less than or equal to. The symbol for that is this. And that is equal to 24. Our answer will then be 3/4 times x is less than or equal to 24. Now try the following. Let's try to translate the following English phrases to sentences or vice versa. For number 1, x plus 5, we can say, or we can read that as the sum of a number and 5, or 5 added to x, and so on. For number 2, we can write, or we can read that as the sum of the product of 4 and 5 and 3, or simply the product of 4 and 5 increased by 3. For number 3, we can state that as a number divided by 2 is equal to negative 7. For number 4, we read that as 4 is less than the quotient of 10 and 2, or 4 is less than 10 halves. Okay. For number 5, 5 less than a number is written as x minus 5. Because if you will remember from our example previously, the word that follows after the word less than is our minuend. Okay, that's why our minuend here is x, which is the unknown number, and our subtrahend is 5. Lastly, for number 6, the product of 2 and 7 is less than or equal to n. We write that as 2 times 7 is less than or equal to n. So those are the examples on how to translate. Please follow the next video for the other terms related to algebra. Bye! Hello again, dear students. Today we move on to the part 2 of our discussion for quarter 2, week 3 in Mathematics 7, which is the introduction to algebra. Here is our most essential learning competency, as well as our reference. And let us start with defining what an algebraic expression is. So an algebraic expression are combinations of variables, numbers, or at least one arithmetic operation. When we say arithmetic operation, those are, or that includes addition, subtraction, multiplication, and division. So here is an example of an algebraic expression. We have 3x plus 5y minus 10. That expression has the following terms. We have 3x, 5y, and 10. These terms are separated by the operations addition and subtraction. So if I'm going to ask you how many terms are there in this algebraic expression, so your answer should be 3 because we have 1, 2, and 3 terms. Another one, 3 and 5 are called numerical coefficients. So we have number 3 here and number 5. Later on, we will define those terms. Then x and y are called literal coefficients of variables. We have here the x and the y. And lastly, negative 10 is called a constant. Let's go over to the definition of terms. So the first one is the word term. It is either a single number or variable, or numbers and variables multiplied together. For example, in number 1, we have the algebraic expression x squared plus 3y plus 5. The terms are again separated by either addition or subtraction. So we have the first term, which is x squared, and then we have 3y, and then the term 5. This expression has 3 terms. For example, number 2, in the expression negative 5y cubed plus 2xy minus 4, the terms are negative 5y cubed. So we consider the sign, which is negative. The second term is 2xy, and the last term is negative 4. Since it follows the operation minus, it means that it carries the sign, which is negative. We also have to take note of the term literal coefficient, which is a variable including its exponent. We use the same examples that we've used a while ago. And we have x squared plus 3y plus 5. The literal coefficient of this term is x squared, so we have to include its exponent, which is 2. And the literal coefficient of this term is y, while for this last term, it has no literal coefficient. So our literal coefficients are only x squared and y. For example number 2, we have the expression negative 5y cubed plus 2xy minus 4. The literal coefficient of this term is y cubed. This term, its literal coefficient is xy, and for the last term, it has no literal coefficient. Number 3, we have the term variable. It is a symbol for unknown numbers. It is usually a letter like X or Y, For in our first examples, we used the letter N, but again, you can use any letter. Next, we have the term numerical coefficient. It is a constant multiplier of the variables in a term. So in this example, our numerical coefficient can be identified per term. So for the first term, our numerical coefficient is 1. How did we get 1? Since we don't have any number there, it means that that is 1 times x squared. Okay, its numerical multiplier is 1, so that is its numerical coefficient. For the second term, our multiplier or numerical coefficient is 3. And then for the last term, we have the numerical coefficient 5. Here is another example. So we have negative 5y cubed plus 2xy minus 4. The numerical coefficient for the first term is negative 5. For the second term, it is positive 2. And for the last term, we have negative 4. Again, we include its negative sign. Next, we have the word constant. It is a symbol which has a fixed numerical value, so it doesn't change. For example, in the expression x squared plus 3y plus 5, the constant there is number 5, since 5 will always be the same even if the value of these two terms changes. The same with number 2, our constant is the third term, which is negative 4. So negative 4 will always be negative 4. It doesn't change in value. Next, we have the degree of each term. It refers to the sum of the exponents of the literal coefficient. For example, in number 1, if we have the literal coefficient x squared, since its exponent is 2, it means that the degree of this is 2. And for 3y, the degree of this is 1. Why? Because y has an exponent of 1, which we do not put anymore. We just write it as 3y, but it has an exponent which is 1. Okay, so the degree of this term is 1, while the degree of this term is 2. For number 2, in negative 5y cubed, the degree is 3, since the exponent of our literal coefficient is 3. For this one, its degree is 2. How did we get 2? Because the exponent of x is 1 and the exponent of y is 1. Since they are together, they are only one term, we have to add its exponents. So 1 plus 1 is equal to 2, which makes its degree 2. And for negative 4, its degree is 0. Why? Because it doesn't have a literal coefficient. It doesn't have a literal coefficient, so its degree is 0. Here is an example, a table with examples. For the first example, we have the expression 3x plus 4. The terms there are 3x and 4. So it has two terms. Next, the literal coefficient is x. We only have x as the literal coefficient. The variable is x again. The numerical coefficients are 3 and 4, while the constant is 4. The highest degree is 1, since the exponent of our literal coefficient here is 1. For example, number 2, we have the expression 2m squared minus 5m minus 2. We first look at the terms. So the first term is 2m squared. So that should be 2m raised to 2. And then the second term is negative 5m. And then we have the third term, negative 2. Again, take note that we have to include if it is negative or positive. Okay, if it follows the minus operation or the subtraction operation, so we have to write that as negative, the term as negative. For the literal coefficients, the literal coefficient for the first term is m squared. For the second term, it is m. And we only have one variable used in this expression, which is letter m. For the numerical coefficients, we have 2, -5, and -2. The constant is the last term, which is -2, and the highest degree that we have is 2. That's why it is our highest degree. Go over the other examples. So here is example number 3. Example number 4. For example number 3, its degree is 3. How did we get that? For the literal coefficient, we have x squared y. Okay, that is our first literal coefficient. The exponent of x is 2. The exponent of y is 1. We have to add those two. So 2 plus 1 is equal to 3. That's why the highest degree for this expression is 3. Next, for example 4, 6m cubed. Okay, so its literal coefficient for the first term is m cubed. That is already our highest degree. That's why the degree of this expression is 3. And for the last one, we have a raised to 7 plus 2a raised to 4 minus 6a plus 2. We have the degree of 7, since our first literal coefficient here is a raised to 7. Okay? Now, we also have the term polynomial. It comes from the word poly, meaning many, and nomial, meaning terms. A polynomial contains 2 or more algebraic terms. It is an algebraic expression that represents a sum of 1 or more terms containing whole number expression on the variables. Again, it contains whole number expression on the variables. For an algebraic expression is not a polynomial if the exponent of the variable is not a whole number. So if the exponent is not a whole number, for example, it is a fraction or an irrational number, we do not consider that as a polynomial. As well as if it is a negative exponent. So that is not a polynomial. For number 2, an expression is not a polynomial if the variable is inside the radical sign. Again, if the variable is inside the radical sign. And for the third factor, which makes an algebraic expression not a polynomial, is that if the variable is in the denominator. Okay. Here are examples of polynomials. For number 1, 4x squared is a polynomial since the degree of the term is a positive integer. Number 2, we have here a polynomial with 2 terms, and the degrees are both positive or whole numbers. For number 3, it is also a polynomial because the only number inside the radical sign is 43, while x is outside. Okay, it is not included inside the radical sign. But for number 4, it is not a polynomial because our variable x is inside the radical sign. And for number 5, we have the expression -7y raised to -3 plus 6y squared minus 12, which makes it not a polynomial because in our conditions a while ago, it is not a polynomial if the exponent of the variable is a negative number. So it should be a positive integer. Okay? 1, 2, and 3 are polynomials, but 4 and 5 are not polynomials. But still, they are considered algebraic expressions. And here are the types of polynomials. First, according to number of terms, we can classify it as monomial, binomial, or trinomial. For monomial, comes from the word mono, which means one. So if you count the terms and there is only one term, you call that as a monomial. Here is an example: 3x, negative 10, 6xy. As for binomial, bi, which means from the prefix bi, which means 2, it means that it has two terms. Okay, here are examples: 2x plus 4y. Our first term is 2x, the second term is 4y. The next one is x to the fourth power minus 3xy. Our first term is x to the fourth power, and the second term is negative 3xy. Okay, negative 3xy. For the third example, we have xy squared plus 6x, so it has two terms as well. And the third classification is trinomial, from the word prefix tri, which means 3. Okay. Examples, we have x to the fourth power plus 3x squared minus 3. We have the first term, second term, and third term. And again, it is separated by addition or subtraction. Here is another example. We have 3y to the fifth power minus 3xy minus 18. And lastly, we have x cubed plus 12x squared plus 9. Now, we can also classify polynomials according to the degree. We've learned about degree a while ago. It refers to the highest exponent of our literal coefficients. Okay, the first classification is a constant, wherein the polynomial is of a degree 0. Linear if the degree is 1, quadratic if the degree is 2, cubic if the degree is 3, quartic if the degree is 4, quintic if the polynomial has a degree of 5, and the next degrees have no universal name yet, so they are just called polynomial of degree 6, 7, 8, 9, and so on. So you identify it as a polynomial of degree 6, 7, and up. Okay. Here are some examples of polynomials with its degree. For the first polynomial, we have 3y to the fifth power minus 3xy minus 18. The degree of our first term is 5. It means that we classify that as a quintic polynomial. For example number 2, we have negative 2x squared y squared plus 3x minus 10. For our first term, we have the literal coefficient 2x squared y squared. We have to add its exponents 2 and 2. The sum is 4. That's why this is a quartic polynomial. The third example, 7a squared. The exponent of the literal coefficient is 2. So our example, or this example, is a quadratic. And for the last one, xy to the third, or xy cubed plus y squared minus 5x squared minus 11. The exponent of this x is 1 and the exponent of y is 3. Since there are only one term, we have to add 1 plus 3 and the sum is 4. Again, this is an example of a quartic polynomial based on the degree. Now, take note that the standard form of polynomial means that the terms are arranged from highest degree to lowest degree. In a polynomial, the leading coefficient is the term with the highest exponent, and leading coefficient is the numerical coefficient of the leading term. Let's look at the table for the examples on how to write polynomials in standard form, as well as identifying its leading term, leading coefficient, degree, type of polynomial according to number of terms, and its classifications according to the degree. For the first example, we have the expression negative 4k squared L plus 3k plus 9L minus 5. The degree of the first term is 3 because we have 4k squared L adding 2 and 1, which is the exponent of L. 2 plus 1 is equal to 3. That's why our degree is 3, which makes it a cubic polynomial. Counting the number of terms, we have 1, 2, 3, and 4. It has 4 terms, which makes it a polynomial based on the number of terms. And let's continue with writing the standard form. The first term is then negative 4k squared L because its degree is 3, followed by 3k with the degree 1, and 9L with the degree 1 as well. We can write 3k and 9L in any order, but since letter K comes first, so we write 3k first, and then followed by 9L minus the constant 5. Having that, we can write the leading term, negative 4k squared L. From that, we can take the leading coefficient, which is negative 4. Next, our next example is negative 3 plus 10x squared. Negative 3 is a constant having the degree of 0, and the degree of our second term is 2 because the exponent of the literal coefficient is 2. That means that 10x squared should come first in order for us to write it in standard form. So 10x squared minus 3 is the standard form. From that, we take the first or the leading term, which is 10x squared, and then the leading coefficient is 10, while the degree of our literal coefficient is again 2. That's why the degree is 2, classifying it as a quadratic polynomial. And since it has 2 terms, so we call it a binomial. Next, for the third example, we have 13a to the 5th power. It has only 1 term, so we call it a monomial. And it is already written in standard form because there is only 1 term. It is also the leading term, and the leading coefficient is 13. The degree of our literal coefficient is 5, so we call it a quintic polynomial. Lastly, we have 5x plus 7x minus 8x cubed plus 1. From that, we can identify 8x cubed or negative 8x cubed as the leading coefficient because its exponent or the exponent of the literal coefficient is 3. The next term is 7x squared with 2 as the exponent or the degree, and then followed by negative 5x followed by plus 1. And then the leading term is then negative 8x cubed. Our leading coefficient is negative 8. The exponent of our literal coefficient is 3, which makes it a cubic polynomial. And the expression has 4 terms, so it is considered a polynomial. I hope that with those examples, you were able to identify and differentiate the different terms in algebra, which we will use in our next discussions. So prepare, because our next lesson will be on evaluating algebraic expressions. Until next time, bye! Hi students! Today we are going to learn the lesson for Math 7 Quarter 2, Week 4, which is evaluating algebraic expressions. By the way, this is teacher Mary Jane. For the most essential learning competency, you are expected to evaluate algebraic expressions for given values of the variables. And the reference is stated or written. Before we start, let us recall what is an algebraic expression. An algebraic expression is an expression that you will see most often once you start algebra. In algebra, we work with variables and numerals. We've learned that a variable is a symbol, usually any letter that represents one or more unknown numbers. Thus, an algebraic expression consists of numbers, variables, and operations. And to evaluate an algebraic expression, we will simply substitute and evaluate using the order of operations, or PEMDAS. So what does it mean by the abbreviation PEMDAS, or by the acronym PEMDAS? P stands for parenthesis, E for exponent, M and D for multiply or divide, A and S for add or subtract. Using that, let us solve the following examples. If we are given the problem 3x plus 9, this is our algebraic expression, and we are going to evaluate it if x is 4. It means that we are going to find its value by substituting x to our variable in our algebraic expression. So for the solution, we copy the given 3x plus 9. Then we substitute the value of x. As you can see, we have written 3 parenthesis 4, or 3 times 4 plus 9. Now we substitute using PEMDAS. We start by multiplying 3 times 4. The product is 12 plus 9. And then we add 12 plus 9. The sum is 21. And that is our final answer. For example number 2, we are given the expression 2y minus 20. What is its value if y is equal to 15? Again, we write the given 2y minus 20, and then we substitute the value of y, which is 15. So we have 2 times 15 minus 20. Then we multiply first 2 and 15. 2 times 15 is equal to 30 minus 20. Using the PEMDAS rule, we subtract and we will obtain 10. That is our final answer. Example 3, we have the expression a plus 5b. Let's find its value if a is equal to 2 and b is equal to 5. Again, let us copy our expression a plus 5b. And then we substitute the values of a and b. So we have 2 plus 5 times 5. Then we apply PEMDAS. So in PEMDAS, multiplication comes first. That's why we will multiply 5 times 5, which is 25. And then we copy 2. So we have 2 plus 25 is equal to 27. Our final answer for example 3 is 27. For example number 4, we have the expression negative 5d plus negative 6u minus 3. We will find its value if d is equal to negative 1 and u is equal to negative 2. Again, we copy our given. Then we substitute. So d, we substitute negative 1. And for u, we have negative 2. And we will have this expression, negative 5 times negative 1 plus negative 6 times negative 2 minus 3. And we simplify using PEMDAS. So you can see we have 2 multiplication expressions that we have to multiply. So we have negative 5 times negative 1 and negative 6 times negative 2. We simplify those and we will obtain 5 plus 12 minus 3. Let's continue by adding 5 plus 12, which is 17, minus 3. And when we subtract 17 minus 3, the final answer is 14. Lastly, for example 5, we have the expression 7a minus b over 2. And the value of a is negative 2, b is 1. When we substitute, we will obtain 7 times negative 2 minus 1 over 2. Then we simplify. 7 times negative 2 is equal to negative 14 minus 1 over 2. We continue by simplifying the numerator. Negative 14 minus 1 is equal to negative 15 over 2. And that is our final answer. So those are the examples for evaluating algebraic expressions. Until our next lesson. Bye! Hello, dear students. Again, we are going to continue our lesson for quarter 2, week 4, which is on addition and subtraction of polynomials. Again, this is teacher Mary J. Our most essential learning competency is for you, dear learners, to be able to add and subtract polynomials. As for the reference, it is the second quarter compendium of notes in Mathematics 7 by the Schools Division of Tarlac Province. In adding polynomials, it involves combining like terms considering the order of operations. For as long as you are careful with the minus sign, you will do just fine. For example, if we are given 4x minus 10 plus the quantity 8x plus 3, we can use two methods to solve for this problem. So let us first look into the horizontal method. For horizontal method, we first copy our given. Then we combine or we remove the parentheses. So we have 4x minus 10 plus 8x plus 3. Then we group like terms, putting together 4x and 8x and negative 10 plus 3. After that, we combine them or we apply the operation. 4x plus 8x is equal to 12x and negative 10 plus 3 is equal to negative 7. Since we cannot combine 12x and negative 7, that means that 12x minus 7 is our final answer. The second method that we can use is the vertical method. So for this method, we just have to align the similar terms. As you can see, 4x and 8x are aligned, and the constants negative 10 and positive 3 are also aligned. Now we start by adding 4x plus 8x, that is equal to 12x, and negative 10 plus 3 is equal to negative 7. We came up with the same answer, which is 12x minus 7. Let's continue with example 2, but we will only focus or we will only use the vertical method. So our given is the quantity 15m minus 3 plus the quantity 2m minus 7. Let us align like terms. 15m and 2m are aligned, and negative 7 and negative 3 are also aligned. We add 15m plus 2m is equal to 13m, and negative 3 plus negative 7 is equal to negative 10. That is our final answer. For example number 3, we have 3x plus 7y plus the quantity 9x minus 5y. Again, we align like terms or similar terms and we add them. 3x plus 9x is equal to 12x and 7y plus negative 5y is equal to 2y. Example 4, this time we are going to add trinomials. We are going to add 2a plus 8b minus 2 plus the quantity 9a minus 6b plus 3. We write them vertically by aligning similar terms. So we have 2a plus 9a is equal to 11a, 8b plus negative 6b is 2b, and negative 2 plus 3 is equal to 1. Therefore, our final answer is 11a plus 2b plus 1. And for the fifth example, we have 11c minus 6d plus 11 plus the quantity 7c plus 5d minus 10. When we align the terms, we will have this, and we can add the terms. 11c plus 7c is equal to 18c. Negative 6d plus 5d is equal to negative 1d, or simply d. And positive 10 plus negative 10 is equal to 0. We can remove 0 and simply write 18c minus d. And that is our final answer for example number 5. So those are the examples. This time we are going to deal with subtracting polynomials. In subtracting polynomials, it is similar to adding polynomials, but we have to change the sign of the subtrahend and proceed to the addition rule. Let's look at the following examples. Example 1, we are going to subtract the quantity 4a plus 1 minus the quantity 2a plus 6. So again, let us look at the two methods. For horizontal method, we write the given. For step 2, we remove the parentheses. Then for step 3, we group like terms. So we have 4a minus 2a and positive 1 and negative 6 together. After that, we apply the operation. 4a minus 2a is equal to 2a, and 1 minus 6 is equal to negative 5. We cannot combine 2a and negative 5, so our final answer is 2a minus 5. Now let us use the same problem, but this time we are going to use the vertical method. For the vertical method, so we write first our given 4a plus negative 2a plus 6. But we have to rewrite by copying our minuend and then change the operation into addition. Then we write the opposite of the signs of our terms for the subtrahend. So from positive 2a, we write negative 2a, and positive 6 will become negative 6. This time we apply addition. So we have 4a plus negative 2a is equal to 2a, and positive 1 plus negative 6 is equal to negative 5. Ow. So again, our final answer is 2a minus 5. For the next examples, we are going to use the vertical method. For example number 2, let us subtract the quantity negative c plus 3d minus negative 2c plus 5d. Using vertical method, let us align the similar terms or like terms. After that, we will copy our minuend, which is negative c plus 3d. Then we change the operation into addition and write the opposite of the signs of the terms of the subtrahend. That's why we will obtain negative c plus 3d plus 2c minus 5d. Then we apply addition, and negative c plus 2c is equal to c, while 3d plus negative 5d is equal to negative 2d. So the final answer is c minus 2d. For example number 3, we have the trinomials 8x minus 3y plus 7 minus 2x plus 4y minus 9. Again, let us align the like terms and then copy the minuend 8x minus 3y plus 7 plus negative 2x minus 4y plus 9. And when we add, the result is 6x minus 7y plus 16. That is the answer to example number 3. For example number 4, we have the quantity 9a minus 2b plus 11 minus the quantity negative a minus 7b plus 8. Let us align them vertically and rewrite. So we have 9a minus 2b plus 11 plus positive a plus 7b minus 8. Then we add 9a plus a, or 9a plus 1a is equal to 10a. Negative 2b plus 7b is equal to 5b. And 11 plus negative 8 is equal to positive 3. So our final answer for example number 4 is 10a plus 5b plus 3. Lastly, for example number 5, we have 2x plus 3y minus 5 minus the quantity 2x minus 4y plus 6. We align and rewrite to obtain 2x plus 3y minus 5 plus negative 2x plus 4y minus 6. And when we add, 2x plus negative 2x is equal to 0, 3y plus 4y is equal to 7y, and negative 5 plus negative 6 is equal to negative 11. Simplifying that, our final answer is 7y minus 11. So those are our examples for addition and subtraction of polynomials. See you on our next lesson, which is on laws of exponents. Bye! Hello once again, dear students. Today we are going to discuss the lessons for week 5 for the second quarter. So we start with part 1, which is the laws of exponents. This is teacher Mary Jane. Here is our most essential learning competency and our reference. For our review, let us identify the parts of the exponential expression below. If we are given 5 squared, we know that 5 is called the base and 2 is called the exponent. And when we expand that, we will have 5 times 5 or 25. We will learn more on that later as we discuss our lesson. Here are the different laws of exponents that we are going to learn. The power rule or n times, the power of powers, the product of a power, the quotient of a power, the law for zero exponent, and law for negative exponent. So let us start with the power rule or n times. For the power rule or n times, let us look at the following examples. So we have the expression 2 squared. And when we expand that, we will obtain 2 times 2. For example number 2, we have the expression 3 cubed. And when we expand that, it can be written as 3 times 3 times 3. And how about for the next example, we will do the opposite. So if you are given 5 times 5 times 5 times 5, how do you think, or how can we write that as an exponential expression? So our base will be 5, and then our exponent is 4, since we are multiplying 5 by itself 4 times. Similarly, let us do the same thing for example number 4. So we have a times a times a times a times a times a. When written as an exponential expression, it can be written as a raised to 6. With that example, what did you observe? How did we determine the base? And how about the exponent? So to answer that, we know that the base, again, refers to the number that we are multiplying to itself, and the exponent refers to the number of times we are multiplying the base by itself. So that is power rule. And for the general rule, we can say that a raised to n is equal to a times a times a times a. So a can be any number or variable. At the same time, n can also be any number or variable. For the second law of exponents, so we have the power of powers. So I want you to check out the first 2 examples, and then you try the next 2 examples. For example 1, we are given the expression 2 cubed the quantity squared. In this example, our base is 2 cubed and our exponent is 2. That means that when we apply the first rule, if we expand it, we will have 2 cubed times 2 cubed. But we can still expand 2 cubed and 2 cubed. So 2 cubed can be written as 2 times 2 times 2, and the other one can also be written as 2 times 2 times 2. So when we rewrite that as an exponential expression, so we will have 2 raised to 6. Now, let's continue with example number 2. We have x raised to 4, the quantity cubed. Just like what we did for the power rule, let us expand first. So we have x raised to 4 times x raised to 4 times x raised to 4. So we multiplied our base by itself 3 times since our exponent is 3. After that, we can expand each term. So x raised to 4 here can be written as x times x times x. The next one, x times x times x. And the last is x times x times x. So when we count all of those and rewrite as an exponential expression, the result is x raised to 12. By now, I know that you have an observation. So do you think there is a way that we can answer 3 or the quantity 3 squared, the quantity squared? Again, 3 squared, the quantity squared. So instead of going over this long process, based on your observation, is there a way that we can answer it right away? Yes. So we can actually multiply our exponents, right? Let's look at example 1 again. So we have 3 and 2. The exponents are 3 and 2. So our final answer, the exponent is 6. It means that we simply multiply those exponents. But we had to copy our base, which is 2, and then multiply the exponents. That's what we did with example number 2. So we can copy the base x and then multiply 4 and 3, and the product is 12. That's why for example 3, here is the long process, but we can simply write or copy 3 and then multiply 2 times 2, and the result is 4. So 3 squared, the quantity squared, is equal to 3 raised to 4. And for example number 4, I know that you already have your answer. So the answer there is simply copy 2 and then multiply 2 times 3. So the exponent is 6. So for the power of powers, we have the rule an, the quantity raised to m, is equal to a raised to n times m. We are multiplying our exponents for this rule. Let's move on to number 3. The third law is the product of a power. So again, I want you to observe the following examples. So for example A, we have x squared times x squared. When we expand x squared, it can be written as x times x. The same thing with x squared, so it is also x times x. So when we rewrite that as an exponential expression, so our answer is x raised to 4. Okay, so here is example B. So we are also multiplying 2 cubed times 2 cubed. So let us expand them. And we will have 2 times 2 times 2 times 2 times 2 times 2. And when we simplify that, we will obtain 2 raised to 6. So what is your observation based on these two examples? Okay, so again, here is example C. So I want you to try to look at the similarities or look for a shorter way for us to skip this method or to skip this step. Okay. So what did you notice about the bases of the expressions we are multiplying? So the bases are actually the same, right? So we can just copy the base. After that, what did we do to our exponents? So for example A, we have added 2 and 2. That's why we obtained 4. For example B, we also copied our base, which is 2. Again, you have to make sure that the bases are the same. Okay? This only applies if the bases are the same. And then we add 3 plus 3. So the exponent is 6. And for example C, our base is x. And we add 6 plus 4, which is equal to 10. So that is 4 product of a power. If we are multiplying terms which have the same bases, so we simply copy the base and add their exponents. So here is the general rule. So a raised to n times a raised to m is equal to a raised to n plus m. For number 4, we have the quotient of a power. So let us simplify the expression below using the first law. What again was our first law? That's right, the power rule or n times. So to simplify this, we have to expand. 4 raised to 7 can be written as 4 times 4 times 4 times 4 times 4 times 4. And 4 raised to 4 can be written as this. After that, we can cancel the 4 fours, and we are left with 3 fours, or 4 times 4 times 4, which can be written as 4 cubed. Okay, next, let's try this example. So what do you think is the result when we divide 3 raised to 5 over 3 cubed? So let us again expand. If we expand that, we will have 3 times 3 times 3 times 3, and then 3 times 3 times 3, and then we will cancel. But there is a shorter way for us to answer. Let us observe our first example. So in this example, we can just copy our base. So again, just like in our previous rule, the base should be the same. So they have the same basis, which is 4. And then what did we do to our exponents? We subtracted them. So 7 minus 4 is equal to 3. That's why the result here, or the final answer, is 4 cubed. With that as a clue, we can do the same by copying the base, which is 3, and then subtract 5 minus 3, and the result is 3 squared. For example B, so again, the bases are the same, so we copy 4 and then subtract 3 minus 2, and the result is 1. But when the exponent is 1, we don't have to write it, so we simply write 4. And how about example C? So of course, that is 5. And then 3 minus 1 is equal to 2. So the final answer for C is 5 squared. Okay, so those are the answers. And let's continue. Here is our general rule. So if we are given a raised to n over a raised to m, we simply subtract our exponents. Let's continue with law number 5. For the fifth law, we have law for zero exponent. Let us simplify the expression below using any law that we've discussed. So what is the result when we divide 2 cubed over 2 cubed? Let us use first the previously discussed one. So we have 2 cubed over 2 cubed, so that can be 2, and then 3 minus 3 is equal to 0. Am I right? Yes. How about if we use the first method wherein we will expand? So let us check. So we have 2 cubed over 2 cubed. And if we are going to expand that, we will have 2 times 2 times 2 over 2 times 2. So times 2 times 2. And we can cancel. After that, we are left with 1. From that, we can say that 2 raised to 0 is equal to 1. They are similar. 2 raised to 0 is equal to 1. So law for zero exponent simply says that a raised to 0 is always equal to 1. Again, so in here we have 2 raised to 0. So if the exponent is 0, it is simply equivalent to 1. but a should not be equal to 0. Remember that a should not be equal to 0. Okay, so here are some examples. So 2 raised to 0, b 100 raised to 0, and cx raised to 0. All of those are equal to 1. So remember, for law for zero exponent, if the base is, or if the exponent is 0, then it is always equal to 1. Okay? And we move on to the last law, which is the law for negative exponent. So let us try simplifying the expression below using any law. Okay, so here is the first law, or first solution. So we have 3 squared over 3 raised to 4. We use the first law, which is the power rule. So we've expanded 3 squared and we obtained 3 times 3. For the denominator, we have 3 times 3 times 3 times 3. And then we cancel what we can cancel. So 3 and 3 can be canceled. So for the numerator, we are left with 1. And for the denominator, we are left with 3 squared. And using another method, which is the law for the quotient of a power. So we've learned that if the bases are the same, we simply copy the base, which is 3, and then subtract our exponent. So 2 minus 4 is equal to negative 2. From those two solutions, we can say that 1 over 3 squared is actually equivalent to 3 raised to negative 2. So that is actually what the law for negative exponent tells us. Okay, so here are some examples. So 2 raised to negative 1 can be written as 1 over 2. How did that happen? So we know that 2 raised to negative 1 can be written as 2 raised to negative 1 over 1. Now to apply the law for negative exponent, we get the reciprocal. So we have 1 over 2 raised to 1. So for our exponent to become negative, we have to get its reciprocal. So the reciprocal of this is 1 over 2 raised to 1, or again, since it's okay if we will not put 1 as an exponent. So 1 over 2, or 1/2, is the answer for letter A. For example B, so we have 5 raised to negative 2. So again, 5 raised to negative 2 is similar to 5 raised to negative 2 over 1. So the reciprocal of that is 1 over 5 squared, but for the law for negative exponent, we simply change the sign of our exponent into positive. So we have 1 over 5 over 2. 1 over 5 squared. And for example C, we have x raised to negative 3. So get the reciprocal to make the exponent positive. So it can be written as 1 over x cubed. Here are more examples for the law for negative exponents. So for example 1, we have a over b raised to negative 1. Since the exponent of a is 1 and the exponent of b is negative 1, so we have to get its reciprocal. It will move to the numerator. That's why it can be written as a times b, or ab. For example 2, we have 2 over x raised to negative 5. Since the exponent of 2 is also positive, so it stays in the numerator. Only x raised to negative 5 will be moved to the numerator. That's why it can be written as 2 times x raised to 5. For number 3, we have c raised to negative 2 and d raised to negative 1. So since this is negative, so for it to be positive, it must move to the denominator. So we have c squared, and then the exponent of t is negative. So for it to be positive, it has to move to the numerator. Okay, so it is d raised to 1 over c squared, or simply d over c squared. For example 4, so the exponent of y is negative. That means that it moves to the denominator. Okay, and the exponent of 4 is 1, so it stays in the denominator. That's why y raised to negative 2 over 4 is equal to 1 over 4y squared. And lastly, for example 5, we have x times y raised to negative 2 over 6 raised to negative 2. So in here, only y has the exponent negative 2. So y raised to negative 2 should move to the denominator for it to be positive. So we have y squared. And then 6 raised to negative 2 should be moved to the numerator for its exponent to be positive. So we have 6 squared. And x remains in the numerator since its exponent is positive 1. So the final answer here is 6 squared x over y squared. So the general rule for the law for negative exponent is a raised to negative n is equal to 1 over a raised to n. That ends our lesson on laws of exponents. So again, our 6 laws are the power rule, or n times, the power of powers, the product of a power, the quotient of a power, the law for zero exponent, and the law for negative exponent. I hope that you continue to watch our next lesson. Goodbye. Hi students. Today we are going to tackle the lesson for quarter 2 week 5 part 2, which is on multiplying and dividing polynomials. Here is our most essential learning competency and reference. We start with multiplying polynomials. As we all know, multiplication can be represented by the signs cross, asterisk, dot, or parenthesis. Now, if we are given the equation 5 times 6 is equal to 30, we call 5 the multiplicand, 6 is called the multiplier, and the answer is called the product. So that is just a review. Now we start by multiplying a monomial by a monomial. So can you still recall what is a monomial? That's correct. A monomial is a polynomial with only one term. So we have here the rule that we will follow. First, we multiply the coefficients, then multiply the variables using the laws of exponents, which we have learned in our previous lesson. For example, we have 3 squared times 3 raised to 6. So for us to find the product of this, we use product of a power. So in product of a power, we simply copy our base, which is 3, and then add our exponents, which is 2 and 6. So 2 plus 6 is equal to 8. That's why the final answer is 3 raised to 8. Here is the next example. How about if we have numbers or numerical coefficients and literal coefficients? So for us to solve this, we multiply 3 and 2, and then we also multiply x raised to 5 times x raised to 7. So for the solution, we have here 3 times 2 times x raised to 5 plus 7. Again, we are using product of a power to solve this part. And simplifying further, 3 times 2 is equal to 6. rate times x raised to 12. So the final answer for example 2 is 6x raised to 12. For example 3, we have b cubed times 5b raised to 7. So the numerical coefficient of our multiplicand is 1. So we have there 1 times 5. And then we have b raised to 3 plus 7. Since in our multiplicand, the exponent is 3. And in the multiplier, the exponent of b is 7. When we solve that, the final answer is 5b raised to 10. Example number 4, we have two variables, b and t. So we use the same procedure. So we multiply first 4 and 2, and then multiply b raised to 1 over b raised to 4, and then multiply d raised to 4 over d raised to 7. And when we multiply that, we have a times b raised to 5 times d raised to 11, or 8b raised to 5 d raised to 11. And for the last example, in multiplying monomial by a monomial, we have 9y squared z raised to 5 times the quantity y raised to 4 z raised to 5. So again, the numerical coefficient of our multiplier is 1. That's why we have 9 times 1 there. And then the exponents of y is 4 and 2, and the exponents of z is 5 and 5. Simplifying, we have 9 times 1 is equal to 9. And then we have y raised to 6, z raised to 10. This time, we move on to multiplying a monomial by a polynomial. So it is important that we have mastered multiplying a monomial by a monomial for us to be able to answer the next examples. So it says there, use the distributive property, then apply the rules in multiplying monomial by monomial. Here is an example. We are multiplying x times the quantity 4x raised to 4 minus x raised to 6. For us to answer that, it says there, we distribute. Okay, we distribute our multiplier, which is x, multiplied by 4x raised to 4, and then x times negative x raised to 6, or we state it as x times 4x raised to 4 minus x times x raised to 6. After that, we solve it by term. We first multiply x times 4x raised to 4, and the result is 4x raised to 5. Next, x times x raised to 6 is equal to x raised to 7. When we combine those two, the final answer is 4x raised to 5 minus x raised to 7. For example number 2, we have a times a trinomial, which is 3a squared plus a minus 7. Again, we distribute a to the terms. We will have 3a squared times a plus a times a minus 7 times a. And when we solve that, the result is 3a squared plus a squared minus 7a. For example number 3, we have 2b times the quantity 3b cubed minus b squared plus 2b minus 4. And when we distribute the multiplier, which is 2b, so we will have this. And when we multiply, we have 6b raised to 4 minus 2b cubed plus 4b squared minus 8b. Now, how about if we are going to multiply a binomial by a binomial? So a binomial has two terms. The most common method that we use is the FOIL method, although you can use the long multiplication method. or the vertical method to solve for this. But for our examples, we will use FOIL. F stands for first terms, O for outer terms, I for inner terms, and L for last terms. And here is an example. Let us use the FOIL method to answer the following examples. For example number 1, we have the binomials x minus 2 times the binomial 3x plus 4. So we first identify the first terms, outer terms, inner terms, and last terms. The first terms are x and 3x. So we write the pair as x times 3x. Next, the outer terms are x and 4. So we pair them up and we have x times 4. Next, the inner terms are negative 2 and 3x, or negative 2 times 3x. And the last terms are negative 2 and 4. And that is negative 2 times 4. After that, we multiply 1 by 1. X times 3x is equal to 3x squared. X times 4 is equal to 4x. Negative 2 times 3x is equal to negative 6x. And negative 2 times 4 is equal to negative 8. Now observe if there are similar terms that we can combine. From this example, we have 4x and negative 6x. They are similar terms, so we add. So we are adding 4x plus negative 6x, or 4x minus 6x, and the result is negative 2x. Means that the simplified form of this is negative 2x. So we combine the results and we have 3x squared minus 2x minus 8. That is the product of x minus 2 times the quantity 3x plus 4. Let's move on to example number 2 as we multiply the quantity 4x plus 8 times the quantity 5x minus 2. Again, we identify the first, outer, inner, and last terms. Using those pairings, we multiply. So 4x times 5x is equal to 20x squared. 4x times negative 2 is negative 8x. 8 times 5x is equal to 40x. 8 times negative 2 is equal to negative 16. And again, we have the similar terms, negative 8x and 40x. We add them and the result is 32x. After that, we combine each term. So we have 20x squared plus 32x minus 16. And here is our third example. We multiply 7a minus 1 times 2a minus 3. Again, we list down our first, outer, inner, and last terms. Then we multiply, and those are the results. After that, we combine like or similar terms. We have 21a plus negative 2a, or negative 21a minus 2a, and that is equal to negative 23a. So for our final answer, we have 14a squared minus 23a plus 3. This time, let us learn how to multiply a polynomial by a polynomial. So it says there, distribute the first term of the first polynomial to each term of the other polynomial. Repeat the procedure of up to the last term and simplify the results by combining similar terms. So for example, we have the quantity a plus 5 times the quantity 3a squared minus 5a minus 10. It means that we have to distribute a times this term, times the second term, and then times the third term. After that, we also multiply 5 times all of our 3 terms. When we do that, we will obtain this. We have a times 3a squared plus a times negative 5a plus a times negative 10 plus 5 times 3a squared plus 5 times negative 5a plus 5 times negative 10. After that, after we have distributed each of the terms, this time we are going to multiply. So 3a cubed minus 5a squared minus 10a plus 15a squared minus 25a minus 50a. Now, we check if there are similar or like terms. In this case, we have the similar terms negative 5a squared and positive 15a squared. We also have negative 10a and negative 25a. So we combine those two. So our first term is 3a cubed. Since there is no similar term to this, so we just copy 3a cubed. Now, when we combine negative 5a squared and 15a squared, the result is 10a squared. And when we combine negative 10a minus 25a, the result is negative 35a. And then we copy the last term, which is negative 50. And that is our final answer, since we cannot combine any of the other terms. So again, our final answer is 3a cubed plus 10a squared minus 35a minus 50. Let's move on to example number 2. This time we have the quantity 2x squared plus 5x minus 3 times the quantity x squared minus 7x plus 12. So when we distribute, we will have this pairings. After that, we multiply each term or each pair. So we have 4x raised to 4 minus 14x cubed plus 24x squared plus 5x cubed plus minus 35x squared plus 60x minus 32 minus 3x squared plus 21x minus 36. And again, we combine like terms. So there is no similar term to 4x raised to 4, so that will be our first term. Then we combine this and this, since their literal coefficients are the same. We also combine 24x squared with negative 35x squared and with negative 3x squared. We also do the same to 60x and 21x. And our last term will be negative 36. So again, our first term is 4x raised to 4. Negative 14x cubed plus 5x cubed is equal to negative 9x cubed. So that is our second term. Then the sum of 24x squared minus 35x squared minus 3x squared is equal to negative 14x squared. So that is our third term. And for our fourth term, the sum of 60x and 21x is 81x. Then we add the last term, which is negative 36. We rewrite, and our final answer is 4x raised to 4 minus 9x cubed minus 14x squared plus 81x minus 36. This time we move on to dividing polynomials. So here are the parts of a division. We have the dividend, the divisor, and the answer is called a quotient. If there is a remainder, then we name it as remainder. And for the long method, the dividend is inside the division symbol, and we have the divisor, the quotient, and the remainder. With that, let us try to divide polynomial by a monomial. So it says there, we divide each term of the polynomial by the given divisor. For example, we have the polynomial 3x cubed plus 6x squared plus 15x. We are going to divide that by the monomial 3x. So what we'll do is to distribute our divisor, which is 3x. So we will have 3x cubed divided by 3x plus 6x squared divided by 3x plus 15x divided by 3x. And we can cancel 3 and 3. As for x cubed over x, we can use the quotient of a power from the loss of exponents that we've learned last time. Okay, so when we do that, we are going to subtract the exponents 3 and 1. So this will be cancelled. We still have a remaining exponent of 2. That's why we have there x squared. For the second term, 6 divided by 3 is equal to 2. So we have there 2. And x squared divided by x is equal to x raised to 1, or simply x. And for the third term, 15 divided by 3 is equal to 5, and x will be cancelled. So that is our final answer for example number 1. For example number 2, we have to divide 8x raised to 4 minus x cubed plus 4x squared minus 16x divided by 4x. So again, we distribute and we will obtain this. Now we divide 1 by 1. So 8x raised to 4 divided by 4x is equal to 2x cubed by dividing 8 and 4, which is equal to 2, and again by subtracting the exponents of x raised to 4 and x raised to 1. For the second term, the numerical coefficient of this is 1, so we cannot cancel 1 and 4, so as is, we will only cancel x in the denominator, and we have a remaining exponent of 2. For the third term, we have x because we've divided 4 and 4, and we have a remaining 1, exponent of 1, after we've subtracted the exponents. And for the last term, we will cancel x, and 16 divided by 4 is equal to 4. That's why our final answer for this example is 23x cubed minus x squared over 4 plus x minus 4. Next, for the third example, we are going to divide 6x cubed y plus 8xy cubed minus 2x squared y squared. We are going to divide that by 2xy. So again, we distribute our divisor and we will have this. So for the first term, 6 divided by 2 is equal to 3. And then x cubed divided by x is equal to x squared. Y and y will be cancelled. Next, 8 divided by 2 is equal to 4. X and x will be cancelled. Y cubed divided by y is equal to y squared. And for the last term, 2 and 2 will be cancelled. X squared divided by x is equal to x, and y squared divided by y is equal to y. That's why our final answer for this example is 3x squared plus 4y squared minus xy. This time, let us learn how to divide a polynomial by a polynomial. So for example, we are going to divide the quantity x to the fourth power plus 4x cubed minus 2x squared minus x plus 1 divided by the quantity x plus 1. So we are going to use the long division method to solve for this problem. So before we start, we must make sure that our divisor, or the terms in our dividend, is arranged from highest exponent to the lowest exponent. Now, in case there is a missing term, we will replace it with 0. So since in this example, we have the exponent of 4, 3, 2, and this is 1, and then this is the constant, so there is no problem. So we proceed with our first step, which is to divide the first term by the first term of our divisor. So x raised to 4 divided by x is equal to x cubed. After that, we are going to multiply x cubed to both of our terms in our divisor. So x cubed times x is equal to x raised to 4. So we are going to align it with x raised to 4. Next, we multiply x cubed by 1, and the result is also x cubed. After that, we subtract. But in subtracting, we are going to add, or we are going to change our operation into addition, and then change the signs of our terms. So this will be negative, and this will also be negative. After that, we can now subtract or add. So we have x raised to 4 plus x plus negative x raised to 4 is equal to 0. So we don't have to put that. This time we subtract, or we add 4x cubed plus negative x cubed. The numerical coefficient of this is 1. So it's like we are subtracting 4 minus 1. That's why the result is 3x cubed. After that, we bring down negative 2x squared. Then we divide 3x cubed divided by x. So 3x cubed divided by x is equal to 3x squared. And again, we multiply 3x squared times x. The result is 3x cubed. And 3x squared times 1 is equal to positive 3x squared. Again, we subtract. This will be addition. And then the sign will be negative. This will also be negative. And if we add that, the result is negative 5x squared. So again, we bring down the next term, which is negative x. Now we divide negative 5x squared by x, and the result is negative 5x. That result will be multiplied to each of these terms. So negative 5x times x is equal to negative 5x squared, and negative 5x times 1 is equal to negative 5x. We subtract. So again, this will be addition. This will be positive, and this will be positive. So this will be, again, 0. And then negative x plus 5x is equal to 4x. We bring down the last term, which is positive 1. Then we divide 4x by x. The result is positive 4. Then we multiply. 4 times x is equal to 4x, and 4 times 1 is equal to 4. So we subtract 4x minus x, or we follow the same process. So this will be addition, negative, and this will be negative. Okay, so 1 plus negative 4 is equal to negative 3. That is now our remainder. So to write our final answer, we write x cubed plus 3x squared minus 5x plus 4, remainder negative 3 over our divisor, which is x plus 1. So that is our final answer. For example number 2, we are going to divide the quantity 2x plus 3 plus 6x cubed minus 5x squared divided by the quantity 2x plus 1. Again, we use the long division method, but we make sure that the terms are arranged from highest to lowest. So we put the first term as 6x cubed, since its degree is 3, followed by negative 5x squared, then 2x, and then the constant 3. After that, we divide 1 by 1. So 6x cubed divided by 2x is equal to 3x squared. Then we multiply 3x squared by 2x. The result is 6x cubed. 3x squared times 1 is equal to positive 3x squared. Then we subtract. So again, this will be addition. This will be negative. And this will be negative. And the result when we add is negative 8x squared. Then we bring down 2x. Next, we divide negative 8x squared divided by 2x, the result is negative 4x. Then we multiply it by 2x again. The result is negative 8x squared. Negative 4x times 1 is equal to negative 4x. Then we subtract. So this will be addition, positive and positive. So when we add, the result is 6x. Then we bring down the last term, which is 3. Now 6x divided by 2x is equal to 3. Then 3 times 2x is equal to 6x. 3 times 1 is equal to 3. Then we subtract. So obviously the answer is 0. But let me show you the solution. So this will be addition, negative and negative. So that is equal to 0. So our final answer is 3x squared minus 4x plus 3. For the third example, we are going to divide the quantity 25n cubed minus 6n plus 5 divided by 5n plus 1. Again, we use this method. So we make sure that the terms are arranged from highest exponent to lowest exponent. However, in this example, if we arrange it, so the exponent of the first term is 3, the next term is supposed to be 6n, and its exponent is 1. That's why we've included a term with 0 as the numerical coefficient and has a literal coefficient, which is n squared, for it to be in order, okay, from highest to lowest. And then the last term is the constant 5. If we are sure that it is arranged in order, so we can now divide. So 25n cubed divided by 5n is equal to 5n squared. And then we multiply that. So 5n squared times 5n is equal to 25n cubed. 5n squared times 1 is equal to 5n squared. We subtract. So this will be addition, negative, and this will be negative. When we add that, the result is negative 5n squared. We bring down negative 6n. And then we divide. So negative 5n squared divided by 5n is equal to negative n. Negative n times 5n is negative 5n squared. Negative n times 1 is equal to negative n. So again, we subtract. This will be addition. This will be positive. And this will be positive. So this is again 0, so we don't have to write. Negative 6n plus n is equal to negative 5n plus our last term, which is 5. So again, we divide. Negative 5n divided by 5n is equal to negative 1. So negative 1 times 5n is equal to negative 5n. Negative 1 times 1 is equal to negative 1. We subtract. So this will be addition. This will be positive. This will be positive. So the result is positive 6. This is now our remainder. So just like what we did in example number 1, so we write the final answer as 5n squared minus n minus 1, remainder 6 over our divisor 5n plus 1. So again, for us to include the remainder, we have to write it as the numerator over the denominator, which is our divisor. So that's it for our lesson in multiplying and dividing polynomials. Thank you so much for listening. Hello and welcome to our lesson for quarter 2, week 6, models and algebraic methods. Here is our most essential learning competency and reference. Let's start with the first one, which is multiplying binomial by a binomial. As we have learned last time, we use FOIL method to multiply binomials. So F stands for first terms, O for outer terms, I for inner terms, and L for last terms. So for example, if we are given the product of x plus 3 times x plus 2, so the first thing that we have to do is to list down the first terms, outer terms, inner terms, or last terms. Or you can use markings such as this. So first terms are x and x, outer terms are x and 2, inner terms are 3 and x, and outer terms are, or the last terms are 3 and 2. After that, we can multiply. So x times x is equal to x squared, x times 2 is equal to 2x, 3 times x is equal to 3x, and 3 times 2 is equal to 6. We combine similar terms. 2x plus 3x is equal to 5x. Then we write the final answer, which is x squared plus 5x plus 6. Here is another example. We have the quantity x minus 4 times the quantity x minus 3. So again, we list down the pairings, and then we multiply. X times x is equal to x squared. X times negative 3 is negative 3x. Negative 4 times x is negative 4x. And negative 4 times negative 3 is equal to 12. We combine the similar terms, negative 3x and negative 4x, and the result is negative 7x. Combining them together, so the final answer is x squared minus 7x plus 12. Now we continue with the product of the sum and difference of two terms. So for this method, so for instance, we are given two binomials and the first and second terms are the same. However, the operation is different. Let's say, for example, the first term is addition and the first multiplier is addition and the second multiplier, the operation is subtraction. So let's try to use first the FOIL method for us to see the result. So those are the combinations. So a times a is equal to a squared. A times negative b is equal to negative ab. B times a is equal to ab. B times negative b is equal to negative b squared. So given that, when we combine this outer and inner terms, the result for that, the answer is 0. So basically, we just have to square the first term minus the square of the second term when we are given this type of a problem. Okay, let's see that in our examples. So for example number 1, we are multiplying the quantity 2x plus 7y times the quantity 2x minus 7y. As you can see, they have the same first terms, which is 2x, and the same second terms, which is 7y. The only difference is the operation. So in here, it is addition. Here, it is subtraction. So instead of using the FOIL method, which is a long solution, we can use this model. Okay, we can use that by squaring only the first term and the second term with the operation, which is subtraction. Okay, so 2x, the quantity squared, minus 7y, the quantity squared. So 2x, the quantity squared, is equal to 4x squared. And 7y, the quantity squared, is equal to 49y squared. So that is our final answer to this example. Example number 2, we will multiply the quantity x plus 3 times the quantity x minus 3. Again, they have the same first and second terms, but this is addition and this is subtraction. So we identify first the first and second terms, which is x and 3. Then we square both. We get the difference of the squares. So we have x the quantity squared, minus 3, the quantity squared. So we have x squared minus 9. That is the answer to example number 2. For example number 3, we have the quantity 3y plus 5 times the quantity 3y minus 5. So our first term is 3y and our second term is 5. So again, using our model, so we just square the first term 3y and minus 5 squared. So the result is 9y squared minus 25. As you can see, these methods are very useful because you don't have to use FOIL method, which is a longer process. We continue with letter C, square of binomials. So here are our models. So when we have this example, so x plus y, the quantity squared. So if the binomial is squared, so you just have to square the first term plus that twice the product of the two terms plus the square of the last term. However, if it is subtraction, so we have x minus y, the quantity squared. The only difference is that the second term or the sign of the second term is negative. Okay, let's look at the examples. So example number 1, we find the product of a plus 3, the quantity squared. So we use this method. The first step is for us to square the first term. Or let us list down first the first and second term. The first term is a, the second term is 3. So there, we square the first term, which is a squared, and then 2 times a times 3, and then plus the square of the last term, which is 3. We simplify. So a, the quantity squared, is equal to a squared. 2 times a is equal to 2a times 3 is equal to 6a. And then 3 squared is equal to 9. So that is it. That's our answer, or that's the product of a plus 3, the quantity squared. Example number 2, we have 3a plus 5, the quantity squared. The first term is 3a, the second term is 5. So we square the first term first, which is 3a, plus 2 times the product of the first and second term plus the square of the last term. So we have 9a squared plus 30a plus 25. That is the answer to example number 2. For example number 3, we are going to find the product of x minus 7, the quantity squared. So this time it is subtraction. That's why the sign of our second term will be negative. Okay, so again, we list down or we identify the first term and second term. The first term is x, the second term is 7. And then we follow this model. So we square the first term minus 2 times the product of the first and second term plus the square of the last, or plus the square of the second term. So x, quantity squared, is equal to x squared. Negative 2 times x times 7 is equal to negative 14x, and 7 squared is equal to 49. Therefore, x minus 7, the quantity squared, is equal to x squared minus 14x plus 49. For the fourth example, we have 3c minus 2d, the quantity squared. Again, we use this method. Our first term is 3c, our second term is 2d. So we square first this first term, minus 2 times the product of the first and second term, plus the square of the second term. The result is 9c squared minus 12cd plus 4d squared. So that is for the square of binomials. We move on to the last one, which is the cube of a binomial. This time, we use this model. So if we have a binomial that is cubed, let's say for example a plus b, the quantity cube, so we are going to use this model. The same for two binomials with the difference of cubes. Okay, as you can see, the only difference is the signs of the second and last term. So if it is positive or if it is addition, so all of the terms are positive. But if we are getting the difference of cubes, so the sign of the second and last term are the second and last terms are negative. Okay, let's look at the examples. So for example number 1, we have to find the product of the quantity x plus 5y, or x plus 5y, the quantity cube. Here is the model that we will use, and we list down, or we identify the first and second terms. Our first term is x, the second term is 5y. Okay, using this model, so we cube the first term, and then 3 times the square of the first term times the second term plus 3 times the first term times the square of the second term plus the cube of the last term, or plus the cube of the second term. Then we simplify. So the first term is x cubed plus 3x squared. So we simplify this first, times 5y plus 3x times, this is 25y squared, plus 125y cubed. Then we multiply the remaining terms. So x cubed plus 15x squared y plus 75xy squared plus 125y cubed. Therefore, x plus 5, the quantity cubed, this should be 3. X plus 5, the quantity cubed, is equal to x cubed plus 15x squared y plus 75xy squared plus 125y cubed. As you can see, this method is easier instead of using FOIL, because if you will use FOIL method, you are going to multiply first x plus 5y times x plus 5y, then you multiply the result to x plus 5y. So that will be a longer solution. Let's continue with the second example. So find the product of x plus 1, the quantity cube. So the first term is x, the second term is 1. The cube of the first term is x, the quantity cube, plus 3 times x, the quantity squared, times 1, plus 3 times x times 1 squared plus 1 cubed. Then we simplify. So this is x cubed. This is equal to 3x squared. This is equal to 3x times 1 plus 1. And then the final answer is x cubed plus 3x squared plus 3x plus 1. Therefore, x plus 1, the quantity cubed, is equal to x cubed plus 3x squared plus 3x plus 1. For the third example, we are getting the cube or difference of cubes. So the sign of the second and last term will be negative. Okay, so here is our solution. So again, we square the first term minus 3 times the square of the first term times the second term plus 3 times the first term times the square of the second term minus the cube of the second term. Okay, simplifying further, this is equal to 8. This is equal to 3 times 4 times 3x. And then 3 times 2 times this is equal to 9x squared minus 27x cubed. Again, that is 8 minus 12 times 3x plus 6 times 9x squared minus 27x cubed. And we have 8 minus 36x plus 54x squared minus 27x cubed. That is equivalent to the cube of 2 minus 3x. For the last example, we have the product, or we find the product of y minus 2, the quantity cube. Our first term is y, our second term is 2, so we follow the same procedure. So we have y cubed minus 3y squared times 2 plus 3y times 2 squared minus 2 cubed. Then we have y cubed minus 3y squared times 2 plus 3y times 4 minus 8. Next, we have y cubed minus 3y squared times 2 plus 3y times 4 minus 8. The final answer is y cubed minus 6y squared plus 12y minus 8. Therefore, y minus 2, the quantity cube, is equal to y cubed minus 6y squared plus 12y minus 8. So those are the important models and algebraic methods that we can use to have to easily multiply polynomials. So instead of using the FOIL method, you can use these models. So that's it for today. Thank you so much for listening.